Hello there, weary peer grader. This is Kevin Bofsar, pretending to sound smart as he explains Physics 2211, Lab 3. Introduction. This lab's focus is orbital motion in space. The key concepts involved here are the first two of Newton's laws, net force and the gravitational force. Newton's first two laws describe inertia, which infers constant velocity where net force is zero, and momentum, which relates force with mass and acceleration. We use these principles to iteratively simulate the object's motion in the model. Net force refers to the sum of all forces on an object, and gravitational force is a formula we'll use to determine the net force of interacting objects in space. In this experiment, we'll find the mass of a black hole using the motion of a star orbiting it. Later, given a planet and also orbiting the black hole and a spaceship, we'll calculate an initial launch velocity necessary to leave the planet, see the black hole, and escape the system. Code, Part 1. First up during the code loop, we implement Newton's second law to calculate momentum from the initial and final velocity values. We'll also take the difference between final and initial for both variables to find dp dt, which also gives us the net force. Then, we'll find the parallel and perpendicular components of dp dt using the formulas shown earlier, and plug in our values in the gravitational force formula to find the mass of the black hole. Each iteration will arrive at a different number here, so our final answer will be the average of them. The aforementioned average is immediately inputted in Part 2, where we also select an arbitrary initial velocity vector for the spaceship in order for it to meet the black hole and escape. This wall of code calculates distance values and uses them in the gravitational formula to find the net force on the planet and the ship. Finally, the velocity and position update formulas to simulate the motion of the planet and the ship. Results. The final mass of the black hole comes out to 9.27 10 to the 33 kilograms, and these are numbers we won't really ask for. The chosen velocity of -4 10 to the 7th and 1.4 10 to the 6th meters per second succeeds at the mission for the ship. Error. In Part 1, the actual mass of the black hole may be different than the average, which was calculated with finite precision between the iterations. This also may have affected the motion simulations in Part 2, which all depended on the mass of the black hole. Furthermore, the values derived from trial and error may be suboptimal, and a better combination may exist. What else? The net force of these objects is not directly observable, so the rate of change of momentum was used instead, which simply depends on the rate of change of velocity, or the acceleration, multiplied by the mass. This makes sense, as is given by Newton's second law. Force is the product of mass and acceleration. Testing concluded with a hypothetical speed of 9 to the 10 to the second power and 9 times 10 to the sixth, which sends the spaceship into a seemingly perfect circular orbit. That's it. Goodbye.